What's up, peoples? This video is intended to help you with things rolling using energy. Previously, we had used dynamics, which required FPDs and a little bit of substitution, but as you know, energy tends to make things easier. So we're going to approach the same kind of problem using energy. And in the past, when we use energy, we've written out the work energy theorem, which is what we're going to do here. We're going to start with initial kinetic energy, initial gravitational potential energy, but now we also have rotational kinetic energy. So K rotational, K-rot, I don't know, initial plus work equals final kinetic plus final potential plus final rotational. All right. The questions that you ask are still the same. It doesn't say that this starts from rest, so we must assume it does. So it doesn't have any initial kinetic energy. It is above height 0, so I'm going to leave the potential energy. But now it comes to rotational energy. So the question that we're going to ask ourselves here, K rotational, is it rotating, yes or no? That's it. Like, that's where you get the rotational energy. Is it rotating, yes or no? Simple question. In the beginning, it is not rotating, so we're going to cross it out. Is there work being done? All right, so this is a big thing. The only reason that this thing rotates is because friction is acting on between the surfaces here, causing it to rotate. It's creating a torque that causes rotation. However, the thing that we need to talk about is friction allows, oh boy, that A did not come out well, allows the object to rotate. That's important. And we're going to sum this up. I can't even spell the word rotate. I must be off my game today. We're going to sum this up at the end of the video, but the initial potential energy, if this thing didn't rotate, it would just slide down. So all that initial potential would become translational kinetic energy. Again, translational means that the center of mass of this disk is moving. However, friction allows the thing to rotate. So some of the initial potential energy is then transformed into rotational energy. It is not doing negative work. It's allowing for the rotation. All right, back to our work energy theorem. We've got, I don't know why it won't give me red. There it is. There's no work done. It is moving in the end. Yes, it is at height 0, and it is rotating. So after this, you just do, like a little mathy math. And let's do it. We've got mgh. So that's mgh would be d sine theta. This is d sine theta, because this length of the incline is in the problem, d. And sine theta is 3/5. So this would be 3/5 of d equals 1/2 mv squared plus 1/2. This is a thin ring, or it's a thin section of pipe. We're going to assume that it's a thin ring, so it's mr squared omega squared. Okay. Well, it says how fast is it traveling? All right. Well, fast is not angular. Fast is translational. So we have this angular velocity here that we don't want, but we do know that omega equals v over r, because you know that we're going to be using v equals rho omega. I've just rearranged it for omega. I could substitute that in here. And first of all, masses are going to go away. So let's get rid of that. I'll rewrite this as 3/5 GD equals 1/2 v squared plus 1/2. Okay, now we have r squared. Omega squared would be v squared over r squared. And I think you'll see here that, oh wow, the r goes away. And now we are just simply left with, sorry, I'm having trouble scrolling down. There we go. We've got, oh boy, 3/5 GD equals 1/2 v squared plus 1/2 v squared is v squared, or v equals square root of 3/5 GD. Pretty simple. I mean, we're just adding another energy, rotational energy. That's all. You know how to do work and energy. Now let's add a little, rotation. All right, let's look at this. We've got two solid disks connected by an axle that has no mass, apparently. There we are. And there's a rope that pulls horizontally on a two-disc system with a force of 50 newtons. What is the angular velocity after it rotates 4 times? Okay, this is a very specific problem that was chosen for a reason. And so we have two solid disks and a rope that pulls with 50 newtons. All right, well, first of all, we're going to need to get the total moment of inertia. So I total is just, there's two disks, and they have the same mass and same radius. So it's just going to be twice 1/2 mr squared. So I total equals, well, m is 3, because the 2 and the 1/2 go away. R would be 0.2 squared meters, sorry. And I didn't do this ahead of time, but we're good. You can bear with me. So we have a total of 0.12 kilogram meter squared. Okay. Truth be told, I can't remember if this problem was intended to be on a fixed axle, where the object here would just rotate around the fixed axle, or if it was on a horizontal surface and it was rotating and also translating, like it was moving forward with that 50 Newton force. Interesting. So I'm going to go with the latter, that it's actually on a surface to make this problem a little bit more challenging. But we're going to do the same thing. We've got initial kinetic energy plus initial potential energy plus initial rotational energy. You could do Kr if you'd like, plus work equals K final plus potential final plus K rotational final. Again, if you want to just do Kr, that's fine. Is it moving in the beginning? I'm going to go with no. Never mentions initial velocity. Is it above height 0? No, it's on height 0. Is it rotating in the beginning? No. Is it moving in the end? Yes. The center of mass will be translating. It's still at a height of 0, and it will be rotating. So if we start off with 0 energy and we end with some energy, that means work had to be done. All right. From class, we should know that work when it comes to torque, sorry, my computer's just like super laggy right now. It's driving me nuts. That work is torque delta theta. That's a terrible torque. We got to do that better. Torque delta theta. The thing rotates 4 times. All right, well, that's pretty easy. 4 rotations times 2 pi radians per rotation equals 8 pi radians. I'll create a number with that later. And the torque is going to be the 50 Newton force acting at a distance of r. All right, so let's get after this. We have 50 newtons acting at a distance r, which I've already forgotten, 0.2. Short-term memory for me there, sorry. So that's 0.2 meters equals 1/2. I've already forgotten the mass. Don't tell anybody. I cannot explain how bad my computer is lagging right now. It's going to drive me crazy. 3 kilograms. This will not be edited. Oh, my God. 3 kilograms v squared plus 1/2 I, which we calculated, 0.12 kilogram meter squared. Oh, did anybody find my math error? I got to go back and fix it. Congratulations if you did, but I just found it because I'm not a smart man. But omega squared. My math error is in the beginning. Oh, my goodness. I'm not editing this. It's 50 newtons acting at a distance of 0.2 meters delta theta, which was 8 pi radians. Oh, my goodness. this. I just went through that whole thing, and I screwed it up. Maybe you caught it. If you did, congratulations. All right, we are solving for, I believe we're solving for angular velocity. So we got to get rid of this v here. And this v here is going to be, as you know, rho omega. All right, so let's get some numbers in a calculator here. Are you ready? That is 10, that's 80 pi. Right? So this is going to be 251 Newton meters / joules, because it was work, equals 1.5 kilograms. We have to replace this with r squared omega squared. R is 0.2 meters squared omega squared plus 0.06 kilogram meter squared omega squared. Combining like terms, the omega squared terms, we have 1.5 times 0.2 squared plus 0.06. And we have got 251 joules equals, that's really weird. We have 0.12 kilogram meter squared. That's weird that that's back to the moment of inertia. Omega squared, solving for omega 251 divided by 0.12. And then we square root that to get an answer, and we get 45.7 radians per second, roughly 7 revolutions per second. And that's it. So the reason this problem was chosen was to actually incorporate work as torque delta theta, which I screwed up in my original math, but you're welcome. Okay, some summary things. As before, I would suggest drawing a picture, labeling your your H equals 0. Easy for me to not say. Also, I would suggest immediately, if possible, when you're doing that if you're given the distance in the problem, that you do H equals d sine theta. So I would do H equals, equals, I'm telling you, like, it's freaking out right now, d sine theta. I would put that in my picture. You're going to write out the work energy theorem, and now we have rotational energy. And the question is, for rotational energy, is it rotating, yes or no? So initially, is it rotating, yes or no? In the end, is it rotating, yes or no? It's that simple. And I just want to remind you that friction doesn't do work. Friction causes the thing to rotate. So instead of all the initial potential energy becoming translational energy, some of it becomes rotational energy. And that's about it. The work done by an external force would be like a rope or something like that, but friction will not do work. Friction is causing it to rotate, allowing some of the initial potential energy to become rotational energy. And you should be, at this point, pretty proficient using rho omega. Ralpha is not going to be a part of this, and also delta S equals wrangle. But that's about it for this video. It was a little shaky with the dodgy computer here. So I'm going to go with 3 out of 5 stars on this one, but I wouldn't change a thing about it.